Hey, what's up, you guys? It's Bailey, and this is Lab 4, Circuits and Capacitors. So, in this lab, our main physics principles are energy conservation and current conservation, and there's some other little guys in there that we also need to focus on. So, we have the loop rule, which is the sum of all the electric potential differences around a loop being equal to zero. So, basically just you have a loop, and when you add everything up, it should add to zero. Charge conservation basically states that the total electric charge in an isolated system is never going to change, which, we've seen these conservation laws hundreds of times. It's always the same, can never be created or destroyed, everything's got to be equal type of stuff. Then we also have the node rule, which says that at any node or junction in an electrical current circuit, the sum of the currents that flow into the junction or node need to be equal to the sum of the currents that flow out of that junction or node. So basically kind of one of those in one, out one type of things. Then we also have steady state, which is basically just where things hold constant. So the name pretty much is just, it explains what it is, steady state constant. So the main objective of this lab was that we were going to predict the behavior of circuits containing resistors in series and parallel. Then use multimeters to measure the actual values of conventional current and potential differences in the circuits. And then looking at the behavior of ohmic resistors and capacitors. And the big things that we're going to be looking at here are the loop rule and charge conservation. So our predicted value was 0.0204 amps, which you get from 3 over 147. And then you have your total potential differences. So from A to B, it's -3. And then from B to C, it's 0. And then from C to D, it's 0.959. And then from D to E, it's 0. And then from E to F, it's 2.041. And then from all the rest of them, it's all 0. And you'll see here that when you add C to D and E to F, that adds up to 3, which when you add that with -3, it cancels out, and then boom, you see the loop rule right there. They're zero. They're zeroed. And so on the far left in the pictures, I have my both ammeters, and then in the middle, it's the ammeter replaced with the voltmeter, and then on the far right, it's the voltmeter replaced with the wire, and then on the bottom, you have in parallel right there. So with the 47 ohm resistor, that equals 47.95 ohms. 100 ohm is 102.05 ohm. And then wire resistance and ammeter resistance are both 0 ohms. So here we have a charged capacitor versus a discharged capacitor. And so with the 10 ohm, we have the charge time equaling 11.01 seconds, and then the time to discharge equaling 12.03 seconds. Then with the 20 ohm, the time to charge is 24.56 seconds, and the time to discharge is 24.98 seconds. And then your RC value is -6.85 seconds, which you get by doing -1 divided by the Y value, I think, in the ln equation. So, questions. What if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? So the answer is that with an ideal ohmmeter, you have 0 internal resistance because this is ideal. But with a real ammeter, you are going to have some small amount of internal resistance. So your overall values would be smaller than the ones we find in this lab because we don't live in an ideal world. Question 2. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. So real-life batteries and capacitors are going to have some internal resistance, and that's going to slow down the charge time of the capacitor. But in an ideal world, the ideal model would reach full charge immediately because it doesn't have that internal resistance. And so this would definitely not happen in real life. Don't forget to subscribe to my channel. I put out new videos every other Sunday. Don't forget to smash that like button. All right. Have a great weekend. Have a great week. Bye.